Hi guys, can you hear me? All right. It's so good to see you again, or I guess half of you. The population has severely thinned out. Okay, so hopefully we won't have another halving by the end of the lecture. So I'm back for a few weeks, and we're going to continue to talk about dynamic programming. That's what I understand. That's what Satish started doing last time. Started talking about essentially dynamic programming. One way to think about it is a sort of a very delicate and smart recursion, where many of the subproblems keep showing up all the time, so you can reuse them. Okay, so it's not just a tree that expands and you're willing to put up with the entire tree, right? So if you think about at the very beginning of this course, we talked about recursive algorithms, and we were basically the master theorem was a way to count the size of the tree, right? The amount of work was happening everywhere. But we weren't paying particular attention to whether certain subtrees were equal to other subtrees, and we could reuse the computation occurring in those subtrees. In fact, usually it wasn't the case. So we really had to pay for the entire tree. In dynamic programming, what we're doing is, but I hear an echo a lot, right? You hear an echo? Can you hear me fine? Okay, it's fine. Dynamic programming, we also have trees, except that now these trees are really big. They're exponential size. So what we want to do is we want to look for structure, recurring subproblems that when we're exploring part of the tree, we say, aha, here's a subproblem. I already solved it earlier, okay? So I don't need to do it again, okay? So it's all about finding subproblems that we can reuse. And I think last time you saw edit distance, right? That was computing the edit distance between two words, right? And today we'll just sort of do more practice with dynamic programming. It's one of those things that the more you practice, the better. There is no sort of particular sort of universal trick. It's just about building some intuition about where dynamic programming can help. Okay, so that's the plan for today. And we'll look at two classical problems. The first has to do with knapsacks, okay? So you didn't start this last time, right? So you just finished with edit distance. Okay. When we look at the knapsack problem, right, so knapsack, I think it literally means it's just like it's a bag that holds things, right? And what we want to do is we have a sort of a pile of things that we want to stash in the bag, right? And each of these have a weight or a volume, you can think about it, and the knapsack has limited capacity, right? And we want to stash the knapsack with the most valuable things from the pile subject to the capacity constraints, okay? So let's look at an example. So we have multiple items, okay? Say that in this case we have 4 items. We're just numbering them 1, 2, 3, 4 just for convenience. And each of them come with a weight and a value. Okay, so the weight, or you can think about it as volume or whatever, is just sort of how much space they take. Okay, so in this case, let's say that item 1 takes up 15 units of weight, and 2, 3, 4, 6, 7, and 8, respectively. Okay, and these weights have some values. Let's say this one is 43, this one is 18, 19, 23. Okay? So these are the things that are sitting in a pile, and our knapsack will have a certain capacity, okay? So a maximum weight that it can carry. And say, in this example, it's going to be 30. Okay, so it's, and the goal is fill your knapsack with kind of most valuable, in the most valuable way. All right, so is the problem clear? Yeah, simple combinatorial problem. So, OK. So let's play with this example for a bit. Now, so I mentioned knapsack within the context of a lecture about dynamic programming. So in a moment, we'll start using dynamic programming. However, we come on the heels of several weeks of greedy algorithms, OK? And I just wanted to mention that if you think about this problem sort of from a fresh state, there is a natural, pretty sort of reasonable greedy algorithm to apply to this problem. Anybody have any suggestions for that? Yeah. What's the ratio? Not the ratio. What's the intuition for that? So the suggestion was look at each item, look at the ratio of value to weight, okay, and pick items with the highest such ratios until sort of your knapsack is full. Why would this be a reasonable thing to do? Yeah.
It maximizes the value per unit of weight. So.
Right. So we have a limited capacity we can take, right? So within that limited capacity, it stands to reason that a reasonable thing to do is just pick items that have the highest ratio of value per unit of weight, right? Because we only have so many units of weight to use, okay? So let's play with that for a moment, and we'll move to dynamic programming. So one idea would be to sort of pick. So by the way, the reason that we're playing first with a non-dynamic programming solution is that actually this algorithm will show up again later in the course. And also because it's good to understand problems from different directions, right? And then we'll see how dynamic programming differs, right? So pick items according to highest ratio of value over weight. Okay, so if we look at the example, we have those four items. We have a certain capacity. Let's compute the ratio for each of these, right? So what is the value? So what is the item with the highest ratio? 2, right? Because it's 18 over 6, that's 3, right? And none of the others have 3, right? Because 15 times 3 would have been 45. That's not good enough. 7 times 3 would have been 21. That's not good enough. And 8 times 3 would have been 24, right? So 2 has this 18 over 6, right? All right, so next up is whom? Yeah, I didn't actually compute the ratios here. So it's either 1 or 4. Anybody want to check on their phone? 4? All right, let's put 4. 23 over 8. Oh, wait. Then we have, who's the other guy? That was 1, right? 43 over 15. And then we have 3, okay? Which is 19 over 7. All right, so if we go in this order, kind of we want to pick them up until we can't, right? So starting with 2, we pick up how much weight? We pick up 15 units of weight. All right, so we have 15 left. So we add 4. We add 8 more units of weight, so we have how much left? You have 8 left, okay? And we pick up 1. So what is it? Sorry. No, sorry, I went sorry. 2, we start out with 8 units of weight. Sorry about that. Jesus. Wait, 6. Okay, yeah, 6. Then we add 4, and that we go to 14, right? And then plus 15, we get to 29, right? 29 is less than 30, so that's good enough. 3, we cannot put it in anymore because we would get to 35, right? So with this one, we're going to get the knapsack 2 4, 1, okay? Which has the weight is going to be 29, and the value is going to be the sum of the values 2, 4, and 1, which is 18 plus 23 plus 43. Okay, so that's 66 plus 18. I hope the answer here, 84. Okay. Please do check the computations and keep me honest. Okay. All right. So that is a knapsack. Okay, so that's what this algorithm gives us. Question. Let's look at another knapsack. Let's look at the knapsack 314. Okay, so what I'm doing is I'm throwing out 2, okay, and I'm putting in 3. Is that fine? Well, 2 and 3 only differ by 1 unit of weight. 3 is 1 unit heavier. We were at 29, right? And now we're at 30, right? So the weight is 30, so this is legit, okay? It's fine. Also notice that 3 was actually at the very end, right? So 2 was actually the winner of the value over weight contest, right? And I'm taking the winner, kicking it out in favor of actually the absolute loser, right? I'm doing this change. What is the value now? Yeah, I agree. I'm not going to try to do computation, but it's 85, which is notably higher than 84, right? So this simple example shows that picking the items according to the very reasonable intuition of highest ratio of value over weight actually does not give always the optimal answer, right? So here's one example where that is the case, where for capacity 30, for items, this ratio approach gave us 84 rather than 85, okay? It doesn't say that 85 is optimal, it just says 84 is not optimal. Okay? So, and I say, well, it's only one off, right? So how bad can it be? Well, so here's another simple example of a knapsack where we're going to apply this same strategy, and we'll be off not by 1 unit of weight. We'll be off by a lot more, okay? Just to drive the point that this ratio, maybe it's really not what we should be doing, okay? So we're going to look at another knapsack. We're going to have only 2 items, so item 1 and item 2. The weight for the first item is going to be 2 million, a very heavy item. So, I don't know, you can think of a very large burrito or something like that. And this one is item 2, instead is a little bit above half as big. Okay, so it's, I don't know, half that burrito plus a grain of rice or something, right? The value of the first one, okay, is going to be 1,999,999. Okay, so just a little under 2 million. And the value of the second one is going to be the same as the weight. Okay, so what's happening here? So in the capacity, I need to say the capacity is going to be precisely 2 million. Okay? Now what's happening here? Let's look at the ratios for these 2 items. So what's the ratio, say, of the second one? 1. Okay, good. What's the ratio of the first one? Less than 1, right? Okay, so what you notice here is that according to the ratio of value over weight, we would pick this one, right? Is that a good choice? No, it's not a good choice, right? It should have been better. It would have been better to pick the first one, right? How much better is the upper choice? A lot, right? We're off by a factor of 2, right? So this is opt, right? This is what let's call it the ratio heuristic gives us. And these two are off by a factor of 2, approximately, right? So the point is that here, this example, we say, well, we're losing 1 unit. Here we're using 1,000,000 units. Okay, so we're off by a factor of 2. Well, too bad. Yes, there's a question.
So where can we increase duplicates?
Excuse me? Right now, I haven't said anything about duplicates, right? So we'll get to that in a moment. Right now, there's 4 items or 2 items, okay? And for each item, there is a single copy, okay? If there are multiple copies of an item, you call them different items. It will be item. Okay. So far, this very reasonable greedy algorithm gives us off by a factor of 2. And yeah, too bad. So we're going to have to do better. Interestingly, actually, this heuristic, we'll see later in this course, can't do worse than 2. So it's actually a non-optimal heuristic that one can prove is actually not terrible. Okay, meaning that this factor of 2 is, it will always achieve a factor of 2. Okay, so it's as bad as it gets. But for today, we want to solve things optimally. Okay, so we're going to put this heuristic aside as a reasonable guess, given as a greedy approach. And so here, kind of a conclusion is that ratio is not optimal. Let's try something else. Okay, just for today, we're just gonna wanna get something optimal. Okay. So now we're gonna. There's a question.
I'm just confused why we can limit it to a ratio of 2. Like in my head, I'm like, oh, what if we set item 2 weight and value to 1?
Sorry, I wanna.
Would that be like a factor?
I wanna change something. Sorry. Well, I didn't write it actually. It's actually a small modification of this strategy.
So you take weight somehow into account?
I don't want to get into it right now, but it's a small modification of this one that does work. All right. So, okay. That's an knapsack problem. Okay. We're going to define it formally now in a general case. And before we solve the actual knapsack problem, we're going to solve something a little bit simpler. Okay, it's called knapsack, as this was brought up, with repetition. Okay, so now, rather than thinking there is a pile of items, there's still going to be a pile of items, a very large pile. And so we're allowed to pick any number of copies from the same item. Okay, so for example, if I go back to the list here, okay, and I'm allowed to pick twice from the same category because there's many copies from each category, what would be a knapsack to pick? Can I beat, for example, this much? This one? Exactly. So what are the 2 items? Item 1 and item 1, right? So here, we could do something better, 86, by just picking twice item 1, right? We would get exactly weight 30, and the value would be 2 times the value of 1, which is 2 times 15, which is 2 times 43, which is 86, right? So why are we considering first this problem? Well, first, sometimes it is an interesting problem when you have lots of items of each type, so might as well consider this variant. But also, the dynamic programming solution to it will be a great stepping stone to dynamic programming to the original problem. Okay? So first, we're going to look at knapsack, so-called with repetition of the items. And we're going to solve it via dynamic programming. All right. So let's just specify the problem in a general form so that we have it. So the input is going to be some capacity for the knapsack. Let's call this capital W for big weight. And then we're also going to get a list of value and weight pairs. So we get V1, W1, V2, W2, and so on and so forth up to Vn, Wn, where Wi is the weight, where Wi is the weight of item I and Vi is its value. Okay? So this is the input to our problem in the general case. Do we agree? Okay. And also in the general case, our output, what is our output going to look like? What is it? Syntactically. Yeah. We really have to just say, I mean, we don't have to repeat things like values and weights. They're part of the input to the problem. We want to make a choice, right, of these things. So how, syntactically, what is a choice? Yes?
List of numbers.
It's a list of numbers, yes. So these numbers are, it's a list of numbers, yes, in, let's say, between 1 and n. But what kind of list of numbers is it? Yeah? Right, so it's like a histogram, right? I'm saying how many I would like of item 1, how many I would like of item 2. Another way to think about it, it's a multi-set. Okay, what is a multi-set? It's a set where you're allowed to have the same element appear multiple times. Okay? Right, so haven't you heard of the term multi-set before? Some of you, okay? Just multi-set is just a set where an item can appear multiple times. And the number of times it appears matters, okay? So this is different from a set where I say the set AA equals a set A because they're the same set, right? But as multi-sets, they're different. AA is a different multi-set. So you can think about multi-sets are just histograms, okay? How many things of each item with no particular attention to order. So one way to write it is that this is just, we want to output a multi-set inside the set 1 through n. Okay? So this is the abstract sort of a formulation of an abstract problem with repetition. Okay. So now we want to solve this problem with dynamic programming. Okay? And so what is the first thing you should think about when you want to apply dynamic programming? Right? What are the subproblems? Right? Okay. So what are the subproblems? Any thoughts? With or without a certain item? Yeah, that's a good place to start. Let's define it. But so these solutions are indexed by what, right? So remember, we have to let's introduce k. Okay, so k is going to be represent our subproblem, but our subproblems are usually indexed by things, right? We have to say we're going to have to build our optimal solution a piece at a time. We want to first solve optimally certain subproblems and take solutions. Optimal solutions to those subproblems and combine them into optimal solutions to the final problem, right? So what should I index? I mean, there are many places you could start from, but yes. For example, capacity, right? Why is that a reasonable thing to index over? Because suppose I were to look at a special case where the capacity is, say, 0, right? What do? You output the empty set, right? That wasn't such a hard problem to solve, right? Okay, maybe it's a bit too degenerate. Let's set the capacity to be 1, right? Probably you can solve it, right? You just look over the things that fit in 1 and you just pick the largest, okay? So this is just to to demonstrate that as capacity becomes smaller, the problem becomes easier, right? So at a high level, we want to sort of leverage knapsack problems solved over smaller capacities in order to solve the knapsack problem over larger capacities. Was that clear? Right? Somehow, as the capacity goes to 0, the hardness of the problem becomes simpler and simpler. Okay, so that's kind of a direction in which you want to move. So let's say we have a certain capacity here, little w. It's just a guess, right? Maybe there's other. Maybe we're going to have to add other parameters to the subproblem parameterization. But let's start with something, right? Suppose that I wanted to solve a knapsack with repetition, okay, of a certain capacity, little w. We want to somehow involve a case invoked on something smaller, right? Because inductively, I should have solved them already optimally, right? So I want to optimally solve a knapsack with capacity little w. How can I rely on optimal solution to smaller knapsacks? Yeah.
Like you choose to take an item on your belt, so you do like knapsack of little w minus say w1 plus, or take like the best option, right? You want to compute the knapsack of w minus w1, w minus w2,
Yeah.
and so on. And then take the best of those.
Almost. Let me take that one as a suggestion, and we're going to fix it, okay? So if I interpret the suggestion correctly, it was, let's take the maximum over I going from 1 to n. Why I going from 1 to n? Because we're going over the items of k of w minus wi, right? Because we're saying, suppose that I were to pick either item 1 or item 2 or item 3, right? This would give me a subproblem where I have lost that much capacity. If I have solved this problem optimally, maybe I've solved this problem optimally. I think there's something missing here, right? So are we, yeah? Yeah, I mean, I picked an item. I should get paid for it, right? So I need to add vi, right? So I'm saying either pick item 1, right? In which case I gain v1, and then certainly I'm now down to a problem which is w minus w1. Which knapsack do I want to complete this to an optimal solution? Well, the optimal one from there onwards, right? Or say maybe item 1 was not the best choice, so let's try item 2, right? This will bring me down to w minus w2. I pick the best choice for that, and I also get v2 sort of in return, right? And these are really all the options, right? Now, notice that because I'm doing this knapsack with repetition, in the subproblem, I don't need to remember that I already picked item 1 or item 2 or item 3, right? There's an infinite number of each items. Okay, so in the subproblems, I don't need to pass the information of my choice. I claim that this actually works. Questions? Are we convinced that this one will give you the optimal knapsack for capacity W? Yes?
How could it occur with W is not offset capacity?
There is not what, sorry?
It's still in the capacity W because we didn't know if we add VI and we can capacity.
So are you worried on the above the capacity or below 0? Above capacity. Well, suppose for a moment that we are convinced that this gives the optimal solution for capacity little w, then what I want is the answer of k given as input capital W, right? And that is the one that I care about. And this one will rely on smaller capacities. Okay? Now, there's a couple of technicalities here I need to make sure of, right? So first, I need to start off I need to make sure that I never invoke this one on negative capacities, right? Because if this one goes negative, I shouldn't have the privilege of getting some value for it, because it doesn't make sense, right? So here, really, I should modify and say that we're only considering things such that W is at least Wi, right? At every recursion, I should only make choices that make sense, right? That's one thing. Another thing is I should start off by saying that at the very bottom, K0 is 0, right? Just to start something. Right? And more generally, anything above 0 where you cannot fit anything specific from the items is still 0, right? All right. But before we get to the algorithm, are we fine with the fact that this sort of way of constructing an optimal solution for W as a function of optimal solutions for things less than W makes sense? Yeah.
So when you say K is 0, you mean K of the set?
And this is not a set. Neither is this. This is an integer that denotes the capacity of my knapsack. So K of 0 says that I have a very, very small knapsack. It has capacity 0. Therefore, the optimal solution for it will be picking the empty set, which has value 0. This one is saying I have a knapsack that has capacity W. Okay? And the optimal value for a knapsack of capacity W is precisely this expression. You take smaller knapsacks for all possible options of either including at the last step any of the items, and you compare sort of what gives you the best option at the last minute, okay? In the last choice. And previously, there were already optimal choices for those capacities, right? Again, because I have repetition, I don't care which items participated in achieving optimality in the sub-choices. Yes? So I didn't understand the start of the question. Try again. Good question. The question is K outputting a knapsack? No. K is outputting the value of the knapsack. And this is analogous to when we were studying, say, shortest paths, okay? In that, you say, oh, we're looking for the shortest path. But wait, you just tell me the length of the shortest path. I wanted the actual shortest path, right? The way you do it is you leave breadcrumbs in your algorithm, like these pointers that you can sort of go back and follow. And once you find the optimal distance, it is because you have left breadcrumbs, you can recover an actual path that achieves that distance. Similarly, in dynamic programming, you have this thing Satish talked about, this underlying DAG, right? Did he talk about this? Yeah, he did, right? So there is this underlying DAG, right, of sub-problems that I'm exploring, right? And at some point, I achieve a certain optimal solution. I can look at the path that I've taken to get there, and that will tell me the solution to the problem. In particular, it will reveal the actual knapsack that satisfies that capacity. Good question. Okay, so let's talk briefly about the running time of this algorithm, okay? Well, it's not an algorithm yet. It's almost. By the time you write a recursion, it's almost an algorithm. Let's just write the algorithm explicitly, just so that we're convinced that there is an algorithm. So the algorithm that sort of is implied by the recursion, you say, OK, set K of 0 to be 0. And then for I, or rather for little w, going from 1 to big W, we're going to now literally compute this expression. And then we're going to return K of W. Now, okay, not much new has happened. The main thing, notice, is that we are going in this order, okay? We're solving first the smaller subproblems so that when we get to the bigger subproblems, we already solved the earlier ones, okay? That's the main thing of this algorithm, yeah?
Does this assume weights are all integer values?
Why would I be assuming that?
Because, I mean, what if there were like objects of weight like 0.87 or something like that? That's a problem.
Ah, okay, sorry for this part. I don't think so. I think that that would be fine. Like, we're not assuming here that I'm exactly matching. Probably, you know, to make that literally work, I probably need to set other things to 0. Like anything that, you know, you cannot fit anything, just set it to 0, right? And the other things will be implied. So given that this is the case, what is the running time? Yeah. Almost. Where is the second W coming from? Yeah, so there's a W coming from here, but inside here, why would I be paying for W? NW. NW. Okay, good. So N times W. All right. Okay, is that a good time? Is NW a good time? Yeah. Excuse me? All of this stuff, these last 3 words, are all about with repetitions. We'll discuss without repetitions in a moment. Is the running time NW good? I claim it's not. Why is it not? Why is it not a good running time? Oh, it's unfortunate, but yeah, I claim it's not a good running time. Yeah. So can N be. You're getting the right point. I mean, I wrote W as a big letter, but maybe N is bigger, right? So, yeah. Well, you're just rephrasing why we're paying. So you're saying, yeah, we have to go through 1, 2, 3, blah, blah, up to capital W. Yes, that's why we have capital W. But why is paying for capital W a bad thing? You're just
ranges of between 1 and big W where it's just the same items over and over.
Yeah, that just means the algorithm gets tired or bored. But I mean, maybe there's ranges where nothing much is happening. Like, for example, that might be the case, for something like that, right? If we run it on this one, there's long swaths of sort of W, W plus 1, W plus 2, W plus 3, where nothing is happening, and we're still kind of paying for that. But I'm asking for something much crisper. Capital W is no good. Why? Yeah. What? The greedy algorithm is faster. Maybe, but it's not optimal. So today we're not looking at it. Yeah. Not quite. I'm looking for something asymptotic. Yeah, back there. W isn't polynomial, okay? Now, look at this. I am given these inputs, okay? This is the input to my problem. Now, what is our gold standard for something to be efficient? Polynomial in the input size, right? So what we want is poly in the input size. What is the input size now? I mean, roughly. N, but more, okay? N? How many bits does it take to represent capital W? Log W, right? I mean, unless you encode it in unary or something, some stupid basis, right? But like in binary, it would be n and log w. But look, here, we're paying exponentially in it, okay? So namely, even an integer that can be represented, I don't know, in like 300 bits, it's not a lot, right? It's this much, right? That's 300 bits. You can write them, right? Like, but the integer represented to it will have 2 to the 300 potentially size, right? Do we want to pay for size 2 to the 300? Hell no, right? So the point is that you want to sort of follow your input size. That's what efficiency is, right? And the point is that this is something called kind of not really polynomial time, but weakly polynomial, which is it's like a complement to the algorithm, right? It's not really polynomial, and in fact, it's not surprising because we'll see later in the course that this problem is so-called NP-complete, okay? Solving knapsacks in time that is polynomial in n and log w is not something that we believe is possible, okay? Yet this algorithm does something interesting, just much slower than that, okay? N times w. Clearly, if w is not big, then it's not a big deal that you pay for w. But if it is big, then it is a big deal, okay? All right. Okay, so now we're going to move to a knapsack without repetition. Are there questions so far? Yeah?
So you're saying that runtime is now good?
And the point is that's life, right? So, now look, it's a cute problem to study. It has a great dynamic programming formulation. The running time you get, is an exponential one, but it's a non-trivial one. In particular, if you just try to match this running time using some other technique, it's not clear what you will do, okay? So applying dynamic programming and getting a good slow algorithm is better than doing nothing and getting a really bad slow algorithm, okay? So in this case, it's just a great combinatorial problem to which to apply dynamic programming to basically bound how bad things can get for optimal solutions, right? The greedy algorithm is efficient, actually. And it's a great approximation algorithm. But if you want an optimal solution, this will give you one. You have to pay for it, okay? And it's a non-trivial solution, right? We did something. We set up dynamic programming. It was doing something. If you try to do something more, not elementary, but more naive, you will not match this running time, okay? You'll get something worse. In particular, one of the things you might try to do is, I don't know, look at all subsets of the items or things like that. You will start paying, for example, 2 to the n, things like that, right? And there's no 2 to the n here, for instance. All right. More questions before we move away from this one to the case of without repetition. Okay, so I'm taking it like very slow because I think it's good to understand all of the steps. Okay. So let's talk about the case without repetition. And what I'm going to do is I'm going to directly modify this board here since it's almost that. Okay? So now we're going to look at knapsack without. So I'm going to underline the fact that without repetition. And sometimes when people just say knapsack, that's really what they mean, okay? Then you have to specify that it's without repetition. So the regular knapsack doesn't have repetition. Via dynamic programming, I think that's great. The input is going to be the same, okay? That's still the input as before. What we wish for, and again, we will fail, is the same as before, n and log w. It's just the output, okay? Now, I still want a list of numbers, but it's not going to be a multiset. What is it going to be? Sorry? Just a set, right? You're not allowed to repeat an item. You pick one up, and it's gone, right? So there was only one copy of it, okay? So you just want to output a set, okay? And you want to maximize the value of that set. Okay? Is it clear how we've changed the... Now there's a formal definition of knapsack. Okay. I think it's time for some Italian. Since you talked about edit distance last week, let's look at two very close words. One is piazza. Is that a software, or where does it come from? Yeah, piazza is actually town square. I guess that's why the company decided to call it piazza. It's just one place where you go and chat, right? And it is, what is the edit distance to pizza? 1, right? But otherwise, they have no particular relation to one another, right? So, I mean, maybe they can both be round, but and to some extent on piazzas, you can think of people or toppings, but like I wanted to focus on this particular so in Italian, you often have these sort of double consonants, and they sound different in the sense that they are, whether you have one consonant or two, they actually make different sounds. So just for the purpose of comparison, this is actually not a word. It is a pronounceable word, so it is like legal to kind of in grammar. But here you would say pizza, right? And this would be pizza, right? There's almost a guttural stop in the middle, so pizza, right? So you almost block your air coming out. Here, it's not piazza, but it's piazza, right? So it's you can think about it as a double T followed by an S, right? Okay, well, so there's so this is not a word, just don't write it. So there are two words that are useful with edit distance. And then I was thinking, here's maybe a harder word that incorporates something that we did study at some point in September. And more food, what else could it be, right? So it starts very similar, but then it continues very different. Oh, it's a long word. It's pizzoccheri. So do you remember, right, we saw the CH before, right? Which is, what sound? K, right? And now there's even a C, another C in front, right? And it just never end, right? So the other C is just reinforcing it. So rather than being pizzoccheri, it's pizzoccheri, right? So there's right? Right? So it's double consonant in both. So what are these things? These things, so I grew up in the mountains. Here's mountain food. It's, I guess, it's, what is it? Yeah, some pasta with cheese, potatoes, and chard. Very tasty, but very heavy. You probably don't see it much abroad because a lot of the Italian culture brought abroad was actually brought from the south. A lot of emigration from the south, so a lot of the Italian-American food comes from Sicily and Calabria, and so they place in the south. It's actually near where I grew up in the mountains, in the border with Switzerland. It's very tasty. But so you can see here, both the double C, and the CH thing. Maybe another place where you find double Z that is interesting is in a word that shows up all the time. How do you pronounce this one? So the J is actually a big trap. So, okay, Utsi is fine. The J is actually a Y. So it's a Yakutsi. And it comes from Latin, where actually J, we call it long I in Italian, ilunga, right? We call it, J is called long I in Italian. And it's a Y. And actually, this is the last name of a family that, of all places, started in Berkeley. There were Italian immigrants that in Berkeley actually set up a company and made this sort of brand that now they sell hot tubs, as you very much know. But I guess in modern Italian, the J depends on the word whether you actually say Y or J, because then there is the sort of other j that came in, the one that you're familiar with. And so then you have to, if it's an ancient Italian word, j, it would be j. Otherwise, it's j. So the current alphabet doesn't actually include the j anymore. So you mostly see it in proper names like this one or city names, things like that. It comes from Latin. So Jakutsi, not Jakutsi. Okay, so enough for that. Wait, are there questions about the words that keep you up at night and like, or haunt you? No? You just don't pay enough attention, maybe, right? You have to worry more, right? Yes? Great, so the question is, how do you pronounce campanile? So campanile is, so campanile is the thing that we have on campus, right? So it literally means bell tower. Campana is bell, and campanile is the structure that holds up the bell. And that one is a really, really simple word. It's maybe one way to really mispronounce it, you could say campanile or whatever, or like camp on the Nile or whatever. I don't know. It's just campanile, so that one doesn't really sort of have any trapdoors. Yes? The pasta that you pronounce like campanile? Maybe carbonara? Huh? You can, if you send it to the TAs, they will send it to me, and then I can bring it up next time. Yes? Favorite pasta? Yeah, I really like pesto a lot. The green sort of thing from pine nuts and then basil. So it's a great sauce to put in pasta. Then the shape of the pasta, I don't care too much. Okay, so let's go back to knapsack. Okay, so without repetition, okay? So let's go to our subproblem. And, this is something that worked before. Maybe it works again, right? It's good to try to recycle. Does it continue working or not? Why does it not work? I agree it doesn't work. Why does it not work? Yeah. Yeah, go. Yeah, I have to remember, right? So suppose, for the sake of argument, that for a particular W that I plug in, it happens to be the case that 1 is the one that gives me sort of, is really the best choice here, right? Now I go in the subproblem, and 1's gone, right? So how does the poor subproblem know that 1 is gone, right? So intuitively, this happens often in dynamic programming. When you impose more structure on the problem, more constraints, sometimes this reflects into having to remember more things. Okay, so here, we're remembering the capacity that we're trying to solve. But now we have to somehow let subproblems know what happened in our earlier decisions, and so on and so forth. Like they have to let their own subproblems know until we sort of get to the bottom. So, okay, a catastrophic choice would be to say, let's remember the subset that we picked so far. Okay? It says, this is the best knapsack with capacity W for a certain set of items out of the n, right? Clearly, as this set tends to the empty set, the problem becomes simpler. And we want to solve, in the end, we would want to kind of return kind of this, right? Capital W and all of the items. However, this is not such a good choice because many subsets, right? We will probably end up somewhere paying for 2 to the n, okay? So typically, you want to try to be kind of stingy with the parameters you introduce in your subproblems. You want it to be kind of as laconic as possible because the fewer options there are, the better. So what is something that lies in between remembering the whole subset and remembering nothing? I claim there's something in between that we could use that is actually not so bad. Almost. Number of items, that's a good one. But if I were to simply do that, I would still not know, I would not be able to communicate to my subproblems which items I've used, right? Because, so the proposal was, remember the number of items, okay? Suppose that I put, let's say, I here, and I mean here the number of items. Oh, let me not use I, because there's already I there. J, number of items. Now, when I go to the subproblems, presumably I will sort of have to invoke j minus 1, right? But then the subproblem doesn't know which item I've used, right? So this is actually insufficient, but it's almost there. Yeah? Encode, so it sounds like very sophisticated. Regardless of encoding, if I want to remember which items I've picked as a subset, that's a lot of options I have to consider, like regardless of how I encode it, right? However, let me offer a suggestion that is very similar to that one. We don't care how the problem gets simpler. What if we just focus on the knapsack, the best knapsack, with the first j items? Okay? So you ask knapsack, capacity W, say with the first item only. Then with the first two items, first 3 items, first 4 items. Certainly the last, when we've used the first n items, well, that's all n items, right? Now I can actually do my subproblems properly, because when I go from j to j minus 1, it is because I have chosen j. And if I didn't, I don't have to reduce it. Okay? So let's together try to do that. Okay? So the proposal is, instead of being number of items, we're going to be with the first j items. So I'm saying, forget all the possible subsets. Let's just try to solve a prefix of the knapsack. Okay? Now, let's see. Now, I shouldn't really look at all the items now, right? So I want to move from solving prefix j to prefix j minus 1, right? So really, my choice right now is not between all possible items. Is either I pick j or I don't pick j. So this max here for I going from 1 to n goes away. Okay? So I'm going to erase this. Okay? So it goes away. And now we're saying, look, we have a knapsack of capacity W on the first j items. Presumably, we want to somewhere invoke subproblems. I claim there are only 2 cases that we have to consider. What are these 2 cases? Yeah, we use j or we don't, right? Say that we don't for a moment. That's the easier case. Suppose we don't use j. What subproblem do we want to solve? K of what? Okay, j minus 1, because we didn't use j. And then W, right? Because we gained something. Right? We're going down, but we didn't lose capacity, right? We're just saying, you know what? Maybe in the optimal solution, I'm just not going to use j, right? And I'm just representing it like that. The other option is the saying that I use j, okay? And in such a case, okay, I use j, right? So there is a problem. But now I have to pay somewhere, right? What happens to my capacity? Minus wj, right? So I actually used it. So now I pick up, of course, vj, right? And I want to pick the maximum of these 2 options. Okay? So I'm saying that for a particular capacity w and a prefix j, either I decide to keep my capacity the same, and I just say, OK, let's see the best I can do with that capacity and 1 item less, specifically the jth one. Or I say, well, how about I use it, then I have to pay in capacity, and I ask, what is the best subproblem there? Okay? Certainly, the best option must be one of these two. Is either I used J or I didn't in the optimal solution. Okay? Crucially, now, what are the number of possible J's here? How many J's can there be? N, right? So here they are. J equals 1, 2, blah, 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 N, right? That's not as many as before if we wanted to keep track of all subsets, right? This would be 2 to the N. OK. So how does the algorithm look like? Let's go to the algorithm. So actually, before we go to the algorithm, are we fine with the recursion? Yes, question. Well, we solved it earlier, the multi-set option, right? So if we had repetition, then we didn't care whether I picked an item or not, right? Now we have only a single copy of each item. Of course, if you have a setting where a certain item doesn't appear infinitely often, it appears 3 times, then just make 3 items, all of them the same weight and the same value, right? OK. All right, so let's look at the algorithm that is this is kind of the end of the creative part. Then the algorithm is somehow mechanically derived from it. So now we have to initialize some base cases, OK? Now we have 2 parameters, right? So we have some more initialization to do. So what are the base cases, the trivial settings? Yeah?
J equals 0.
When J equals 0, OK, so that means that K1, 0 equals K2, 0 equals blah, 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 up to K of capital W, 0 equals what? 0, right? So we're just saying that regardless of your capacity, whether it is 1, 2, 3, up to capital W, if you are not picking any items, it's a 0 prefix, then clearly you can only produce an empty set, and your best thing you can do is 0, right? So that's one thing. OK, that's great. But there is another type of boundary constraint. What is it? Yeah? Yeah, W equals 0, and the other coordinate, whatever, right? K0j for any j equals also 0. OK? This is just good sanity checks. OK? This is just saying whatever prefix you want to look at, if you have no capacity, well, there's nothing you can do anyways, right? So just set it to 0. OK, fine. Then we have to eventually, sorry, there's something I need to fix up there. So what we want is K of capital W and N, OK? And let me remove this one, which doesn't belong anymore. All right, so we want is capital WN, right? So it means that we have to have solved already subproblems for smaller w and smaller n, OK? So let's kind of make some space here. In fact, let me make a lot of space. Not because the algorithm is complicated, just so it's convenient. All right. So how many loops are there? 2, right? So one is over W, right? One parameter of the subproblem. And the other one is over J. So for j going from 1 to n. Okay? Now, it doesn't really matter in which order w and j go. It does matter, however, that in either of them, you're going up. Okay? You're going from easier to harder. Okay? So it is important in either loop that you go from smaller w to larger w and from smaller j to larger j. Okay? Why? Because every time you have a particular w and a particular j, you will have to rely to things that depend on smaller w and smaller j. Okay? And actually, I want to change these loops. Sorry. It does matter because of that. Sorry, there's a small subtle point. Sometimes we want the same w, but a smaller j. Right? So it means that we should have solved. No, it's fine. It's actually fine. Never mind. You can change them. And either change the loop here. I think you can. Unless I'm self-confusing, it should be fine. OK. So now, just like before, if we sort of pick up something that will make us go sort of sub-zero capacity, we should discard it. OK? So if wj is greater than w, then I'm just going to set k of wj to be k of wj minus 1. Right? So in saying I'm picking up something, it doesn't fit anyways, so just whatever, just don't pick it up. Just do the best you could have done without it. Anyways, it doesn't fit. Otherwise, if wj is no bigger than w, then we have this case that we wrote up there. K of wj is the maximum of two cases. One case is when I do nothing. I mean, not do nothing. I just don't pick j. And the other one is where I pick it up, and I have to pay for it in capacity, and then I get the corresponding value gain. OK? Again, what I wrote here is the same as there is above. OK? And then I return k of capital W and small n. OK? Now, this algorithm is simply traversing the subproblem space in such a way that by the time you're solving a subproblem, you have already solved all the necessary previous subproblems. Visually, again, I'm sure Satish also showed it in his lecture, you can think about it as a grid. Why a grid? Because we have two parameters, w and n, right? So here there are the w problems, and here are the n problems, OK? And this grid is a DAG, where the nodes are the subproblems, and what we want is this bottom right answer, OK? And each of these values depends on previous things, OK? And we are solving. This algorithm is basically moving from the top left to the bottom right such that every time you have some intermediate problem, it only depends on things sort of further up to the left. You have them already, right? And so this is sort of the underlying DAG that we're exploring using this algorithm. Now, when you visualize this DAG, it also tells you something about the running time of the algorithm, which is sort of, you can also tell already from here, and this is just a more visual way to view it. What is the cost of running this algorithm? But J is not really like an input to the problem, right? So there's n of them. So J can only ranges between 1 and n. So yeah, just Wn, right? Because think about it. We have an outer loop, W, an inner loop, n, and within each iteration, we're doing a constant amount of work. Another way to view it is that we are basically traversing all of this DAG. This DAG has size W times n. And to process a node in the DAG, it costs us something that is related to the in degree, right? So how many things go into it, which is constant. Okay, right? Because you see here, I only depend on 2 possible sub-problems. There's 2. So the running time is, again, n times w. Okay? So it is the same running time that we obtained for the other version of this problem. Okay? And just like the other problem, it is NP complete. And just like the other problem, this is weakly polynomial running time. Okay? It's not really polynomial for the reasons that we were saying here, that really we want to pay log w. Okay? But is it clear that the running time is nw? Okay. The visualization of the problems that we're exploring, is it also clear? Is this picture making sense? The nodes in the graph represent particular subproblems. The edges represent dependencies, okay? They represent dependencies of which other subproblems we must have solved before we solve that particular node. In general, if you visualize a dynamic programming solution, it will look like something like this. If it has more parameters, it might be in 3D, right? It might be like less pretty, right? But roughly speaking, the running time of your algorithm will be the number of nodes times the in degree. Okay? Why? Because you have to process all the nodes, and processing each node requires a number of work that is proportional to the in degree. Of course, this depends on the operations that you're doing, right? If your combiner here is very expensive, maybe it might not be times the in degree. Maybe it might be times the in degree squared, or whatever, right? So here, we're not doing any sort of interesting combination. But in general, for most dynamic programming, when you combine the subproblems, there's not a whole lot going on. Next time, we'll see an example where sort of the combiner, maybe it's not as trivial, but most of the time it is pretty trivial. Okay. Let me see if there's more I wanted to say about this. Good. So today, we covered 2 algorithms. Okay, it was knapsack without repetition, with repetition. There were 2 very different types of dynamic programming solutions with the same running time. Okay. Next time we'll continue with more examples of dynamic programming.